Okay, sorry about that, guys. I was having some problems there with the Zoom, but it looks like it's working now. So not too late here. So let's get going. Let's just jump right back into what we were doing last week. So first of all, I hope you guys had a good fall break. So we're uh, finishing up with chapter 4. I don't know if we'll finish it today, but if we don't finish it today, we'll finish it on Thursday, and hopefully have some time on Thursday to do a review. But like I usually do, I did post a review recording already, so so there's a pretty nice review there available for you. Okay, so yeah, we are in week 10 here out of 16, so getting to the end here of the semester. We're at the end of the 4th chapter, so yeah, and we'll be here pretty soon. Um, so yeah, let's not lose any more time here. Let's get going with this. So I think where we finished off last week was with our hypothesis testing. So we had learned about the t distribution, and we were using the t distribution to do hypothesis testing for means. So so let's just jump right back into that and practice with another example or two of these. Um, so this is on page 129 of the lecture notes. We're looking at diet supplements. This is kind of a big deal, uh, right? Huge industry. And how do we go about testing to see if it actually works, right? They claim that it works, and who knows if it works, right? Well, part of the process is to do hypothesis testing, especially if it's something that's approved by the FDA. I don't know if dietary supplements need to be approved by the FDA, but anyway, typical medication approved by the FDA does go through hypothesis testing before it's brought to the market. So let's imagine how that would work. So there's a manufacturer. They claim that the product will help people lose weight, and so to prove this, they get a sample of 50 adult males. And so these are males ages 20 to 74. Uh, and they take the supplement, and they do this for 8 weeks. And then they look to see what the weight loss is. Okay, so the average weight loss for these 50 adult males is 0.9 pounds. Okay, so that's the average, and that's a sample, so we call it X bar. And but not everybody loses the same amount of weight. Some are going to lose more, some are going to lose less. And so there's spread in the sample, and we measure that spread with the standard deviation, so S, right? So that spread is 1.2 pounds. So we want to test the hypothesis that the dietary supplement actually results in weight loss. And so if it's if it's causing weight loss, then the mean weight loss will be more than 0. Okay, and we'll go with the typical 0.05 level of significance here. So alpha equals 0.05. Right. So how would we state the hypotheses? Well, the null is the skeptic's hypothesis. The alternative is the researcher's hypothesis. Okay, and then we have to think about what the parameter is that we're testing. So this is quantitative data, right? Because we're counting the number of pounds that are lost. So since it's quantitative, we're thinking about mu, which is the mean. So what exactly is the mean? This would be the average weight loss if all adult males in the population took this weight loss supplement for 8 weeks. Okay, so it's kind of an unusual population, but in theory, we could give this to all adult males for 8 weeks and measure their weight loss. Right? It'll never happen, of course, because lots of people don't want to take it, but in theory, there would be some average weight loss, and that's what we're trying to make an inference about. Okay, so the parameter is mu. Okay, and so this is I think the third or maybe even fourth type of hypothesis test you've done. So by now writing out these hypotheses should be pretty straightforward for you, I think. The null is always the hypothesis of equality, and the alternative is the hypothesis of inequality. So if mu is the mean or average weight loss, then what would the skeptic's hypothesis be? The skeptic is going to say, well, it doesn't work. right? So if it doesn't work, then the mean weight loss would be 0. The researcher's hypothesis, and so we could think of this as the researcher for the dietary supplement company, is that it does work, right? So it should be probably a right-tailed test here. And it's definitely giving us clues there saying that it's more than, right? So it's a right-tailed test. And so how do we test them? Well, we have our data set, right? Or at least the summary statistics. So X bar is 0.9. 0.9 is not 0. It is indeed more than 0. So we do have evidence in favor of the alternative, but how strong is that evidence? I mean, at first glance, that does not look very strong. It's less than a pound on average, but the hypothesis isn't testing how much of a weight loss. We're not trying to estimate the average weight loss. We're just trying to see if there is some weight loss that occurs. Okay, so even if it's very little weight that's lost, it could still, end up rejecting the null. Okay, so before we jump into the test, we have to make sure that the conditions are met, right? So remember, we have our 3 conditions, and those are here on your formula card. You don't need to memorize these, but you'll recognize them from all of the other tests we've done, right? We need randomness, we need independence, and then we need a large enough sample, right? So those are the 3 we're testing. Those are the 3 we're looking for and checking. So it does explicitly say random. So we say it says random. Either the parent population is normal or we have a large enough sample. Okay, the rule of thumb is 30. So they did a sample of 50 here, so n equals 50. So 50 is more than 30. So we'd say 50 is greater than or equal to 30. So check and check. Then the third one there, we have to make sure that we have independence. We don't want all of these guys coming from the same family or the same town, right? We want it spread out. The theory is that the people are independent of each other and not influencing each other. Okay, so the rule of thumb is as long as the sample is less than 5% of the population, we'll be good. And so it's the same inequality you've solved at least a couple dozen times by now. We have to make sure that 50 is less than 5% of the population. So we solve that inequality like that, and that's 1,000. And so what is the population? Well, it's probably all adult males in the country, so definitely there's more than 1,000 of those. Okay, so alpha is 0.05. It's stated here. On the exam, I always try to state that. I mean, my intention is to state it. If I forget to leave that, if I forget to put alpha in, then it's your choice, and I would typically choose 0.05. So then, so we're ready to go. These 3 being met here tell us that the distribution requirements have been met, so we can use that t-distribution to test the hypotheses. Okay, so we'll jump over into GeoGebra at that point. And test it, right? So I think we did at least one of these in GeoGebra last week. So we go to the toggle, the 3 dots, probability calculator. Okay, and then we go to the statistics panel. We've been here many times, and to the dropdown. And by this point in the semester, we've done several of these. And so that's why I always try to go through this like a process of elimination, because after a while there's lots of different options. So let's see, what are we doing? We're not doing an estimate. Those are confidence intervals, right? So all of these are out down here, and we never do the goodness of fit test or the chi-square test. So those don't really apply. So it's one of these up here. We're doing a hypothesis test, right? So what kind of data do we have? Well, as we pointed out, this is quantitative. So we're working with means, okay? And so for our class, we never do like a z-test of a mean, and that's because we very, very typically will not know what sigma is. So that puts us either into the t-test of a mean or t-test difference of means. Well, there's just one sample here. It's not like we're comparing the population of females to males or something like that. There's just one population we're looking at, and that's the adult males. So this would be a t-test of a mean. Okay. So then we put in the null value of 0. The alternative is that there is some weight loss that occurs. So it's greater than. Then we put in the mean, or x bar, the sample mean. Remember, that was the 0.9. And then for the sample standard deviation, we had a 1.2. And then there was a fairly small sample of 50. And there we go. Okay, so the t-score is 5.3, which indicates that it's more than 5 standard errors above the null value. Okay, and so we know once you get past 2 or 3 standard errors, things are getting unusual, right? If the null is true, right? And so basically, we're pretty sure that the null is not true. And so we reject the null in favor of the alternative. And the p-value there, it says it's 0. And it's not really 0, probably. It's probably a little bit more than 0. And the reason it's reporting 0 is because I have it set to 3 decimal places of rounding. I don't like that. I usually do 15. And so, so if we come back up here and readjust the rounding, we can see, yeah, it's not exactly 0, but it's pretty small, right? 0.000001 for the p-value, right? So we have the test statistic there, 5.3, the t-score, and then the p-value. So let's write those down, and then we can make our decision here. So the test statistic t equals 5.303, and then the p-value equals 0.12345514. Okay, and so like we've always done since the very beginning of the course, we compare the p-value to alpha. Okay, so alpha here is 0.05, and obviously the p-value is less than alpha. The p-value here is much less than alpha, which means we're going to reject the null. We do not think that the weight loss is 0. Okay, and when we reject a null, it's always in favor of the alternative. So we do think that there's some weight loss going on here. Okay, so there is sufficient evidence to conclude that the alternative is true. Okay, so the formal decision is reject, but we also want to have that final statement where we put it into context, right? So, and so how would we say that? Well, we would say that the males who take the supplement will have a mean weight loss more than 0, something like that. Okay, so notice we're not saying how much it's going to be. That's the job for the confidence interval. The confidence interval estimates how much that weight loss is going to be. All we've done here is establish that it works. Okay, there is weight loss going on. Okay, all right. Now, way back a couple of chapters ago, we talked about statistical significance versus practical significance. It's been a while, but I did plant that idea. Well, I hope I planted that idea in your minds a while back. It is in the book, so and in the homework. So this, when we reject the null, we're rejecting because it's statistically significant. And if you remember, statistically significant has a very precise definition. It means the p-value is less than alpha. Okay, so there's statistically significant results, but then we want to think about it from a practical perspective, right? So there's statistical significance and then there's practical significance. And so if you look at that, it says a mean weight loss of 0.9 pounds. Yeah, that might in theory be statistically significant, but it's not really practically significant, right? I mean, I don't think anybody would, take these supplements for 8 weeks if they thought they were only going to lose 1 pound, right? Maybe somebody would, but I don't, I think most people would think that that's not really worthwhile, right? So I would say no. While it is statistically significant, I would say it is not practically significant. Okay, and so the statistically significant is a very objective idea. It's just p-value less than alpha. Practical significance is a little bit more subjective. It's a little bit more in the eye of the beholder. I don't know, maybe losing 1 pound would be worth it to some people, but but from I think for most people, definitely me, I wouldn't want to do that for 8 weeks just to lose 1 pound. Okay. All right, great. So it's another example of how this works, and then it's also something to think about when it comes to pharmaceuticals and vitamins, and especially things that don't go through like an FDA process. You can sort of learn how to fake the system a little bit, right? I mean, yeah, they're not lying. We do have sufficient evidence to conclude that there's weight loss going on, but they probably wouldn't tell you how little that weight loss might be, right? So it's something to think about. Okay. So I want you guys to try one here, and then we need to move on into our last section of chapter 4. Let's do one more hypothesis test. I want you guys to get some practice here before we move on. Let me know if you have any questions about that example. There's lots of surveys that are done all the time by various companies, institutes. The government does lots of surveys. Social scientists, marketers, they're interested in all sorts of facets and aspects of everyday life. And this is one of those big surveys that's done. It's called the American Time Use Survey, and that and they're interested in all sorts of different things, maybe like TV usage, right? And so this was an interesting problem. They're looking at time spent watching television, and then they're trying to see if that's been influenced by time spent on the internet. Okay, so the average American spends 154.8 minutes per day watching television, so that's a little bit more than 2.5 hours on watching television. And then along comes the internet, right? And they're trying to see if internet usage changes the amount of time spent watching TV, right? Most people use the internet, right? And then so if you're spending time on the internet, maybe that takes away time from watching television. Okay, so this example probably would have been that the way I think about it is it's kind of an older example. Because like everybody uses the internet now, or almost everybody, right? I mean, it's very, very common to use the internet. It's hard to imagine a lot of people that are not using it at least sometimes, right? I mean, it's just so ubiquitous. So this idea of internet users, it's like it's almost everybody now, right? So I kind of like to imagine this study being done back when the internet was becoming more common, right? So you have people watching television, right? And then the internet becomes more common. And so people are spending time on the internet now. Does that mean that they watch less TV? Okay. Or do they just keep watching the same amount of TV and just spend more time, on the internet, right? So it is possible, right? So that's the idea. And so the mean for TV time is 154.8. And then we're going to have a survey of 50 internet users. Okay. And we're going to see how much time that subset of the population spends watching television, right? So these internet users, they have an average, these 50 have an average television time of 138.7 minutes. but not all of them watch the same amount of TV, right? Some people watch a lot more, some people watch a lot less. So there's spread there in that sample, and we measure the spread with the sample standard deviation. So 76.5 minutes. Okay. And then, so what are the hypotheses? Well, the time spent watching television is a count of the number of minutes that are spent watching TV. So it's quantitative, which means we're looking at mu. Okay, everything in chapter 4 is mu, right? But um, on the final, it won't be like that, right? I mean, it could be mu or p. So the null is the hypothesis of equality, and then the alternative is an inequality. And so the idea is, okay, well, if you take the subset of people who use the internet, maybe they're giving up some of their TV time for their internet time, right? But maybe not. Maybe they keep watching the same amount of TV, but they are just finding other time to devote to the internet, right? Maybe they just stay up later, on their cell phone kind of thing, right? Uh, so the skeptic says that we shouldn't assume that internet users are different than everyone else, right? So the null is that it's 154.8, and then the alternative is that it's less than that, right? Okay, so um, so I'd like you to try this. I'm tempted to just do this myself, but I think it would be nice for you to practice just a little bit with the software here. So you need to go through those three steps there. Then you'll go to GeoGebra for the test statistic and the p-value. And once you have that p-value, you compare it to the level of significance, and you can decide if you're going to reject or fail to reject. So I'll go quiet for about 4 or 5 minutes and let you guys work on that. Practice here a little bit. We'll come back together at about 12:06 and work through this one together, okay? got a question over here in the chat. Yes, I will show you again how to change the rounding in GeoGebra. Okay, so to change the rounding in GeoGebra, it's a little bit funny. We have to hit the gear over here on the left. And once you hit that gear on the left, it opens up a gear on the right. And so you hit the gear on the right, and then it should take you to this rounding place. So I always put mine on 15. It's a little bit of an eyesore, but at least I don't have to worry about rounding problems. And so once I do that, then I hit the save, and it just keeps it in there. Does that help, Shoshana? Good, you bet. All right, let's have a look at this problem here. So do people who actually use the internet, do they watch less television than everyone else? And again, great, Sarai's got it. And yeah, that looks exactly correct. We're going to fail to reject. Perfect. So the idea is, do internet users watch less TV than non-internet users? And nowadays, it's like, who doesn't use the internet? So I'm kind of imagining this study was done maybe like 20 years ago, and before the internet was quite as, ubiquitous as it is now. But anyway, so let's see, alpha here is 0.05. Okay, so the test statistic will be the t-score. And so let's refresh GeoGebra here. Go to the toggle, the three dots, and to the drop down. So it's t-test of a mean. So the null is that internet users are just like everyone else. There's nothing really, unusual or interesting about them. Then we go less than for the alternative. So let's look at that sample data real quick. It does look like there might be something to this, right? The mean is 138.7. That 138.7 is not 154.8. It is indeed less than that. It's about 15 minutes less or so, 16. So is that statistically significant? That's what we're trying to figure out. And Sarai already said, no, it's not. And I agree. The results here are not conclusive. So the mean, we put in the 138.7 sample mean. We put in their standard deviation, 76.5. And then there were 50 here. Let's see, why am I getting different numbers? Oh, that's it, yeah. Okay, so the t here, negative 1.49, the p-value 0.07. Okay, so let's write that down. So we have the t-score, which is the test statistic of negative 1.49. So we're a little bit less than 2 standard errors away from the null value. So we're probably, wouldn't be unusual to get this if the null is true. And then more specifically, the p-value here is 0.0716, alpha 0.05. So the p-value is more than alpha. So since the p-value is more than alpha, we fail to reject. That's our formal decision. It's not our final, word on it. But we want to put this into more kind of plain language. So when we fail to reject, let's fail to reject. We're failing to reject because there is insufficient evidence to conclude that the alternative is true, right? So there's insufficient evidence to conclude that internet users watch less TV than non-internet users. Okay, so that's a little bit sad, right? It just means that people really like their TV and they're willing to, even when they're using the internet, they're still going to, devote pretty much the same amount of time to watching TV. So they must be carving out time from other things, right? Like maybe staying up later at night, reading the internet on their phone or something. Okay, good. let's redo this. And so sometimes these hypothetical examples are nice. They help us to think about, what would happen if we had slightly different situations. And so what we're going to do is we're going to imagine, let's say instead of this being a sample of 50, what if we'd had a slightly larger sample size? Let's say maybe we had 100 instead of 50, and we still ended up with the same sample mean and uh, the same standard deviation. What do you think the impact of the larger sample size would be? Okay, so we're holding everything constant with this scenario except for the sample size. What would happen to the p-value? How would it impact the results of the hypothesis test? Okay, so again, we're going to imagine instead of 50, we had done this with 100 internet users, and it came back with the same sample mean and same standard deviation. Okay, what do you think would happen with the p-value? Well, if it's a larger sample, then it's more information, right? And so if we have the same sample mean and the same standard deviation, I think we can probably guess what would happen to the p-value here, right? So if I'm just going to come in here and I'm going to change this one thing, and I think you can see here, and I think it intuitively makes sense, right? If you have a sample size of 100, it's harder for the X bar to bounce around that far, right? And so the t-score actually, the magnitude of it is larger. Here we actually more than 2 standard errors away. And look at that, p-value actually goes down, which means we can reject, okay? And so that's another aspect of hypothesis testing to be aware of. If you really want to reject the null, right? If you want to have statistically significant results, one thing you can do is have a larger sample, right? And so I don't want you guys to be cynical about hypothesis testing, but I do want you to be aware of ways that the game, can be kind of manipulated and played a little bit, right? So again, that p-value went from like 0.07 down to 0.02 by doubling the sample size. And so it's just something to be aware of, with research. If they have a large enough sample, you can really cut that p-value down and get statistically significant results. Okay, so just something to be aware of with this, right? So what we would say here is with a larger sample size, we get a smaller p-value, or at least we can. Okay, so something to consider. All right. So 2 more things here. A lot of stuff in this chapter. Let's see the question up here. Okay, does this apply to any hypothesis test? Yeah, I mean, well, it's not just that we had a larger sample size, it's that we had a larger sample size and we had the same X bar and standard deviation. But yeah, in general, all of the things being equal, Armand, the larger the sample size, the smaller the p-value. So yeah, it is, it's kind of a, again, I don't want you to be cynical about it, but it is something to consider uh, with hypothesis testing. Good. So let's, I wanted to jump over into the homework for one problem. There's one thing we need to consider when we have a small sample size. And so it is here in the notes, but we didn't put an example problem in, so that's why I want to show you the lecture notes. So I want to jump back up here to the top of page 124. This was something we didn't talk about yet, and it's for the case where we don't have a very large sample. Okay, so this plot, it's called the normal probability plot. It was developed for small sample sizes. Okay, so if you have less than 30, and the underlying population, if we don't know if we don't know that it's normal, and we have a small sample, then we're in we have a bit of a problem on our hands, right? So what statisticians have invented, what they've created here, it's a plot that's used to detect if a small sample probably has come from a normal distribution or not. Okay, and this happens a lot. Imagine if you're doing quality control testing for a car company, right? So, when they develop new cars, they have to crash test cars, and that's expensive, right? I mean, if you have a $75,000 Jeep and you have to crash test them, you don't want to crash test more than you need, right? So we'd like to be able to do these kinds of tests on the smallest possible sample size. We still want to have statistically significant results, but we don't want to crash any more cars than is required, right? At least from the perspective of the auto manufacturer. So these techniques here, this plot, the normal probability plot, is what we can use for the case where we have a small sample size. So let me read this. It says it's another method for checking the assumption of normality. And the idea is they take the sample data, the small sample, and they plot it versus a theoretical normal distribution. Okay, and so when you do that, you get this thing called the normal quantile plot or normal probability plot. It has a few different names. And the theory is if the sample comes from a normal distribution, then when you plot it versus the normal distribution, it should fall pretty close to this straight line. Okay, and so if it falls away from that straight line, then it's probably not coming from a normal distribution. Okay, so I want you to be aware of this. And unfortunately, we didn't really have a good problem in the homework. I'm sorry, in the lecture notes for this. So that's why I'm jumping over to the homework for a little bit. And so this comes from 4.2b, question 6. Okay, so this is 4.2b, question 6 in the homework. Okay, and so again, this is our normal probability plot, and it's mostly useful for the case where we have a small sample size. So let's read this problem together. So it says a random sample of 25 people were asked who were at a large concert venue. A random sample of 25 people who were at a large concert venue. And so there's at least 5,000 people there to watch a pop idol were asked their age. Okay, so we're trying to get an idea of kind of the average customer, right? So the sample mean was 25.1 years old. The sample standard deviation was 12.1. And because the sample is small, they use a normal probability plot. Okay, so that's what this is over here, the normal probability plot and the box plot. Okay, so if we were to do a confidence interval for the average age of people at this concert, or a hypothesis test, we would have to check the conditions, right? And so what are the conditions? Well, they're here on our formula card. Come back over here, right? We have to check for randomness, independent observations, and then either it comes from a normal population or the sample size is more than 30. Okay, so let's go through that. So do we have a random sample? Yes, it says there's a random sample, right? So it is a random sample. Then we have to make sure that the people in that sample are independent of each other. We don't want 25, friends who know each other at this concert. We want to have, a broader sample, right, across the population. The population here is people at this concert. So 25 should be less than 5% of 5,000, right? I mean, I think just kind of common sense, right? So, but we can check that. If I go 25 divided by 5,000, that's less than 1%. That's 0.5%, right? So we're good there. So if you randomly sample 25 people from 5,000 people, they're more or less going to be independent of each other. Okay, so we've got 2 of the 3 requirements. The third requirement is either the sample size is large enough, more than 30, or it's coming from a normal distribution. Okay, well, there's a bit of a problem. 25 is too small, right? So it's not too small if it's coming from an already normal distribution, but we don't know that the age distribution there is normally distributed. Okay, so that's where we would go to the normal probability plot. Okay, and so there's a lot of details behind the scenes on the normal probability plot. What you need to know is that the theory is as long as the points are fairly close to a straight line and don't deviate from the straight line there, then the underlying distribution would be normal. Okay, so I don't think that's what we're seeing here. Okay, it looks like we've got some points here that fall pretty far below the line, and some other points over here below the line. And if we look at the box plot of the sample, I think we can tell that this is looking probably a little bit right skewed. Okay, so if we take the evidence from the normal probability plot and we combine it with evidence from the box plot, I think what we see here is, unfortunately, the population is likely not normal. Okay, so it's looking like the age here, age distribution is probably not normally distributed. And unfortunately, we're not going to be able to use these techniques that we've developed here in chapter 4 for this particular data set. Okay, so I just wanted to show you this problem because, well, I mean, this probability plot is very important for us. Okay. All right, so that's the normal probability plot. And then the very last thing here before we get into 4.3, we need to talk about the sample size problem. Okay, so let's go back to our lecture notes here. And there's a bit of jumping around. I just have a slightly different preferred order that I like to go in for this section. And so let's come back over here. I've bounced around here a little bit, and we're back on page 126. And I want to consider this problem here. Okay, so on page 126, we're looking at this exercise here. It's a Gallup poll, and they want to estimate the number of books, the average number of books read by Americans. Okay, and so what they want to do is create a confidence interval for this, right? This is what Gallup does all the time. They're taking samples and they're using those samples to create confidence intervals. And so before you create the confidence interval, you need a sample, right? And before you get a sample, you need to know how many people to talk to. They don't just start calling people and getting data and then stopping when they run out of money or time, or they feel good about it, right? They have a target sample size in mind before they even start, right? Calling people. And you'll remember doing this in chapter 3, right? We had a sample size problems in chapter 3. Same thing holds for chapter 4. We also have a sample size issue, right? So this was the chapter 3 sample size stuff. Okay, so that was chapter 3 for categorical data. Here in chapter 4, we also have the same sample size problem. Okay, now formulas are a little bit different because it's a different kind of data, different distribution and everything, but very similar idea. You need to know how many people to talk to before you start with your project, right? And so here's the formula, and mostly it just comes from rearranging the margin of error formula. And so let's use that. Let's pull that formula over and apply it here to this problem. So I'm just going to write that formula down over here. So it's a minimum sample, so it's n greater than or equal. If you hit the minimum, then if you go over the minimum, it's not like it's a problem if you have more information. So that's why we call it the minimum. As long as you have this many or more, you should be good. Okay, so how does this work? Well, we need a confidence level. So 95% confidence is a very common level for these, kind of social data, political opinion, kind of surveys that they do. So we're going to have we want to create a 95% confidence interval. We also need to know how broad of an interval we're comfortable with, right? And so that's something you plan at the beginning, right? You know, okay, as long as we're within 4 books or so of the actual mean, we'll be good, right? So it's basically saying how wide of an interval we can live with. All other things being equal, we want a narrower interval, but you know, we live in the real world. There's costs, right, associated with this, and so you know, we're on a budget, so you know, so it's a trade-off, right? And so we'll go with a margin of error here of 4 books. Okay, so that's our margin of error. Then the formula also calls for a standard deviation. Okay, so it's a little bit unusual. How would we know the standard deviation if we don't know the mean? Okay, so that's where like a pilot study would come in. So you can imagine we've done some kind of small initial survey that indicates that the standard deviation is about 16.6. Okay, right? Because not everybody reads the same number of books, right? Some people read a lot, some people read, you know, very little, right? And so there's spread there. And so let's see, let's imagine what's going on here. I know that the average number of books read by Americans, it can't be below 0, right? You can't read a negative number of books in a year. And if we're talking about the average for everybody, you know, like there has to be some upper bound, right? Um, I know a person who claims to read a book every day, and you know that's kind of amazing to me. But you know, certainly the average person isn't going to be reading more than 365 books in a year. It's you know, so certainly it's got to be between 0 and 365, right? Um, so so there's my interval, right? But the problem with that interval is that it's so wide, it's really useless, right? So we want a tighter interval, right? So we know that mu is in there somewhere, and we're going to get an x bar, right? A sample, and then we're going to put a margin of error on both sides of x bar, right? Same story. We've been, same scenario that we've been working with in the last couple chapters here, right? So the margin of error is 4, confidence level is 95, standard deviation 16.6. So we can go right to the formula here. Okay, so the margin of error is 4, standard deviation is 16.6. And then what is our confidence level? That's the Z star. The Z star is associated with the confidence level. And that's going to be on our table. So you might even have that one just memorized by now. So 95% confidence means we have to go out about 2 standard deviations, more precisely 1.96. So we'll have our Z star there of 1.96. And then don't forget to square the whole thing. Okay, so we're going to go 1.96 times 16.6. Okay, then we divide by 4, and then we square it. Okay, so we're looking at about 66.16. Okay, so n has to be greater than or equal to that number. So if we round it down to 66, we wouldn't have enough, right? Because we've got to be at least 66.16. So we're going to round that up to 67. Okay, so you'll need to contact at least 67 Americans and 67 people that participate, right? And they'll tell you how many books they remember reading in the previous year. Okay, so with those 67 people, you can create that desired confidence interval. Okay. All right, so that takes us to the end of our single sample statistics. And so here in 4.3, in the next subsection, in the next section of chapter 4, we're going to do something interesting. We're going to start comparing data across 2 different groups. Okay, so let's see here. Yeah, great, definitely. Yeah, this is something that's confusing to people. Why do we not round down to 66? I mean, because usually when we round, we round to the nearest whole number, but it's all about this 0.16 here. Okay, to get that desired confidence interval, you need at least 66.16, right? So really there's only two options, 66 or 67. And where is 66.16? It's about right here, right? So there's 66.16. Well, if you need to be greater than or equal to that number, we can create like an interval, right? An algebraic interval there of values, right? What is the smallest number that falls in that interval? Well, it's 67, right? So it's all about this last little bit over there. If that's not 0, then you have to always round up to the next whole number. Does that help, Armand? It would be a real shame to conduct this study and then at the end you find out, oh, I was one person short of my desired sample size, right? So we'll always have to round that number up a little bit. Good. All right. So yeah, we've got 20 minutes here. Let's get through as much of 4.3 as we can. And so at this point, we've done a lot of different kinds of inference, right? We've estimated means and proportions. We've tested means and proportions. What we're going to do in 4.3 is more means, but the scenario's changed a little bit. Here, we want to compare the mean from one group to the mean of another group. Okay, and isn't that something that we are constantly doing, right? We're comparing one group of people to another group of people, right? We compare people in California to people in Colorado, right? Or we compare, Canada to the U.S. or something like that, right? And so that's the next step here in our development of introductory statistics is learning how to compare quantitative data across groups. So one group to another. Okay, and so the first step is description, right? Is descriptive. How do we describe and compare across two groups? Then after we talk about describing, we'll talk about inference, right? So we always have to start with the description side, the descriptive statistics. So what is our go-to for comparing quantitative data across two groups? It's the side-by-side box plot. Okay, so back to box plots. You guys know box plots, and there's not really much new theory here or much new technique. All we're going to do is we're going to put two box plots or more. Sometimes you'll see three or several groups that are being simultaneously compared. So we're just going to take two or more box plots and put them on the same axis, and we'll use those box plots to compare the populations or to compare the two samples. And so not really, too much new here. It's the same old box plot. It's just used to compare two populations. So for example, we have two colleges here. We have college A and we have college B. Okay, so students will take the ACT typically towards the end of high school, right? So it's a standardized college admissions kind of exam. And so we take all the students at college A and we create a box plot for them. Okay, so score on the ACT, that's quantitative. So we can use a box plot. Box plots for quantitative data. And then college B, that's also quantitative, right? Their ACT scores. So we take all of the students at college B, we create a box plot for them, and then we compare the two colleges. And this is a super useful technique for comparing two things. Okay, so let's do this. The 5-number summary for college A. Well, you remember the 5-number summary. The box is made of Q1, Q2, and Q3. So it looks like Q1 there is 23. Q2 is the median, 24. Q3, it looks approximately like 25. And then the other two numbers of the 5-number summary are the min and the max. We don't have any outliers here, so the whiskers there do extend out to mins and maxes. And so this is obviously a made-up data set, but sometimes they're nice for kind of learning about an idea at first. So there's our 5-number summary for college A. If we do the same for college B, so we have a minimum of 25 for college B, and then their Q1 is 26, their Q2 appears to be about 27, their Q3 30, and the max scored there as 32. And so with the two box plots with the 5-number summary, we can make some observations about the two colleges, right? College B has a higher median than college A. So the average student for college B did better on the ACT than the average student for college A, right? College A has less variation than college B. Okay, so the scores for college A are, a little bit more compact. So the students are more similar, right? Whereas at college B, they have a wider range of students, right? And then when it comes to symmetry, obviously college A is more symmetric than college B. College B is right skewed, whereas college A is actually perfectly symmetrical, right? Because it's made up data, but sometimes it's nice to have made up data to get the idea across at first. Okay, so that's how we describe data across two populations as with the side-by-side box plot. So not, actually nothing really too new there. What is new is when we do inference across two populations. Okay, so the next thing is confidence intervals. Okay, so let's say you're trying to compare workers in Utah to workers in Colorado, right? So you've got two different populations, and we want to see what the difference is between those two populations. Okay, so we want to do maybe a confidence interval. Yeah. So how would that work? Okay, well, we would begin with some kind of point estimate. And so if we're looking at a difference of two means, we're going to have x1 bar minus x2 bar. Okay, so we'll have a sample from our first population, we'll have a sample from the second population, and if we're trying to figure out the difference between the two values for the whole population, we would take the same difference for the two samples, right? So we'll have x bar 1 minus x bar 2. And what that'll do is it'll help us estimate the difference between the two population means, mu1 and mu2. Okay, all right, so just like with any other confidence interval that we do, there's a lot of background, right, information, important assumptions that are made, right, and formulas, etc. I'm not gonna like, I'm just gonna skip this for a little bit. I think it just makes more sense if we jump right into a problem and just kind of get the feel for it, and then we'll come back and we'll go through all of the theoretical considerations and details. Okay, so I just think it works better if we jump right into a problem, and then we'll come back and make sure we check all of the important details. Okay. And the reason we can jump right into this is because we've done so many confidence intervals now that I think it just works. Okay, so let's jump right into this example here on page 132. And so again, we're comparing quantitative data across two different groups. And so this data set was looking at the age of actresses versus the age of leading actors. Okay, and so these are major motion pictures. Okay, so we're thinking of like the big Hollywood blockbuster movies, and then so think about all of those big blockbuster movies. Most of them are going to have leading actors and actresses, right? And so maybe not everyone, but typically there's like a leading actor and there's a leading actress, right? I mean, if you look at say the Academy Awards, right? Those are kind of just sort of set categories, right? So, maybe not every movie has a leading actress or leading actor, but that's pretty typical, right? And so the idea is there a difference in age between, the average leading actress and the average age for leading actor? Okay, so Does that question make sense? And if so, if somebody just stopped you on the street and asked you that question, you think back to all the movies you've seen, you think about like, who are the most famous actresses and most famous actors? Is there any sort of difference in the age? For me, I would probably say, yeah. I mean, I can imagine like all of these older actors that there's even in their like 50s and 60s, they're still acting, and then maybe fewer actresses, right? But who knows, right? Maybe it's the same, and so that's what we're trying to figure out here. And so what we have is a sample. It's a pretty large sample. We have 84 actresses, and again, these are leading actresses, so like the super famous ones, who are and so you basically take like 84 of these major films, you identify the leading actress, and you record her age, right? And so the average is 35.6 for that group. So we have X bar, and there's two different groups, right? So there's different ways we can write this. We can say X bar 1, or we could say X bar F. Just depend, just use some subscript that will help distinguish the two groups here. So we might say actress there. Okay, so for these 84 randomly selected ones, the average age is 35.6. But some are younger, some are older, right? And so we do have some spread there. And the average spread there is about 11.3. If we look at the histogram, right, age is quantitative, so we can plot this with the histogram. It does appear that it's right skewed. Okay, and remember, the theory is that either it's coming from a normal distribution or the sample size is large enough. So that's pretty obviously not coming from a normal distribution. But it's okay because we have a large sample, 84, right? That's more than 30. So we're probably good there. Let's look over at the actors. So we do the same thing. We've got a sample of 84 major motion picture films, and we identify the leading actor, if there is one, for each of those movies. And so the average age of those randomly selected ones is 44.7. Okay, so that's another sample mean. And so maybe we could say X bar actor, right, for the males. Okay, or you could say X bar 1, X bar 2, you could say X bar F, X bar M, just some kind of subscript there to distinguish the two, right? And then some, of course, are older than 44.7, some are younger, so we have spread there, and that's measured with the standard deviation. Good. If we look at the histogram, we also see what appears to be some right skew there. So we don't have the data coming from a normal population, but that should be okay because we have pretty large samples here. They're both more than 30. So 84 is more than 30 there. Okay. So what are the hypotheses? Well, actually, before I get to the hypotheses, let me draw a picture here. We don't have a ton of space, so let me draw it right here. What is going on here? We've got two populations now, don't we? We have all of the leading actresses. So what is the population? We're taking all of the major motion pictures, right, that pretty much have ever been done, and we're identifying all the leading actresses from those movies. That's one population. So how many of those are there? How many major motion pictures are there every year? I don't know. I just don't have a number. Probably at least 20 or so, right? I would imagine. And how long has Hollywood been doing these movies? For a while now, right? Probably at least, I don't know, 50 or 100 years. So, there's probably, let's say, probably at least a couple thousand, right, of these movies that have been done, these major motion pictures. What about for the actors? So our other population here is the leading actors. Okay, and so we have a sample of the leading actresses. and we have a sample of the leading actors. Okay, so the idea is we're trying to see if there's a difference in the average age for leading actress, leading actor, right? In other words, basically, what it comes down to is do the actors have kind of a longer career maybe than the actresses, right? Um, that I think that's what it's coming down to here. So how would we write out the hypotheses? Well, we actually have two parameters here, right? We have the average age for actresses, and we have the average age for actors. Okay, and so there's two parameters, right? And so there's a couple ways we can write this. I think the easiest way to be introduced to this is to say, well, there's leading actress uh, uh, mean, right? And then there's the leading actor mean. So the null, kind of the skeptic's hypothesis, is that that they're equal to each other, right? If they're equal, then that's great, but there's nothing really left to investigate, right? It's just that's the way it is, and there's nothing really to look into. It's when there's a difference that we have more work to do, right? And so so that's what the alternative hypothesis is that there's some inequality here. Okay, and so which one is it? Is it greater than? Is it less than? Is it not equal to? Typically, the default is a two-tailed test. So if you didn't watch a lot of movies and you weren't really thinking about this very much, you'd probably just want to do a two-tailed test. But it does say that we suspect it's younger, right? So that word there, younger, is pushing us towards the left-tailed test, right? Okay, so this is a perfectly fine way of writing it out. I do want to point out that there's another way of writing each of these, and the second way is a little bit better, I think, for thinking about confidence intervals, which we'll have to do on Thursday. So if we look at this equation, this is an equation, right? Something equal is something. If I subtract mu actor from both sides, I'm going to get an equivalent equation, but it's going to look a little bit different. It's going to say mu actress minus mu actor equals 0. Okay, so mu actress minus mu actor is the difference between the mean ages, right? And so if that difference is equal to 0, then that means that they're the same average, right? So it's an equivalent way of saying the same thing, right? So these two equations here are equivalent. And in some ways, I like the one on the left better. Other ways, I like the one on the right better. Okay, so I like to, so I'll typically use like both of them, and the second one especially for confidence intervals. Okay, so on your exam, you can write either one or both if you want, and they'll both get you 100% on your hypothesis test. We can do the same for the alternative. Okay, I can subtract mu actor from both sides. Okay, and if I did that, that would be mu actors minus mu actor is less than 0. What does that mean? Well, it means that the mean average of actors is more than the mean age of actresses, right? If you subtract those two and you get a negative number, then that's equivalent to being less than 0, right? Okay, so so there's a lot that's the same here, but there is something that's different, right? We now have two populations and we now have two samples, right? And so we take the two samples, right? We take these two here, we get an X bar from each one, and then we use those, to make an inference about the population means, right? The actual average actor's age and the actual average actor age, right? Okay, so yeah, we should understand kind of the basic idea, but some of the details are going to be a little bit different. Okay. Unfortunately, we'll have to pause here and talk. We'll have to finish this one up on Thursday. Okay. So So we're doing fine with the calendar. We have Thursday blocked off as a review day anyway. So we'll take about 30 minutes on Thursday to finish off the new stuff, and that'll give us maybe about an hour to review on Thursday, which will be good. So let's see here. Let's see, I've got a question over here in the chat. Okay, yeah, Haley, let me just conclude with everything else, and then I'll look at that question. So if you can hang out for just a little bit, I can answer that question for you. Okay, so yeah, Thursday we'll finish off chapter 4. We'll get a nice little review in. Probably not, like a full review, but I do have that recorded review there for you. Then next week, exam 3 will open. It'll open on Monday, and it'll be open for 3 days next week. Okay, and so yeah, we're making steady progress here. Done with chapter 4 almost, and then just 2 chapters after that. So yeah, just keep an eye on the calendar. If you have any questions from the homework, let me know. I'm going to go ahead and jump into this question over here from Haley, unless there's other questions. So yeah, so the question, let's see here. Okay, thanks, Armand. The question's from 3.2b, number 11. So if you want to hang around and go through that, you're more than welcome to do that. So this is 3.2b, question 11. Did you mean 4.2b by any chance? Because I'm not seeing a question 11 on 3.2b. Let's see here. No worries. So this one right here, Haley, with the SAT scores. Okay. So we're doing some educational research, okay, and we're looking at SAT scores of students at Ivy League colleges. Okay, so the standard deviation is known to be 250 points. And then we want to estimate the average SAT scores of students at the college, okay, at this Ivy League college, right? So like Harvard or Yale or something, right? So they're, they actually do this a lot. Education is a big it's an important thing, and lots of people are thinking about it, and so we're curious about how this college compares to this college, and etc., right? The state of education. And so anyway, it's something that's of interest to a lot of people. So what is the average SAT score at this college, right? So Raina wants to use a 90% confidence interval. How many students does she need to have in her sample? Right, unless you work at that college, you're not really going to have a list of everybody's SAT scores, right? So if you can't get that list, then you're going to have to do a sample. So how would we do this? Well, let's let me do something real quick so I can write on this a little bit more easily. Okay, so it's a minimum sample size. So we need the sample size formula. Let me pull that up here. And so it's basically that very similar to the problem we did in class today. So that's good. We'll get a little more practice here. Here we are. So here's our formula. Okay, so So Raina wants a 90% confidence interval. And so what, so we use our formula, so the n greater than or equal to z star. What is S? That's the standard deviation, so it's 250. And then the margin of error, we want to be within 25 points of the actual average. Okay. We'd like to even be better than that, but there's always the, kind of the consideration of cost, right? And so it's a trade-off, and so we'll go with 25 points here. Okay, what's Z star? Well, if we want 90% confidence, then we come over here to our table. 90% is is a Z-score of 1.65. Okay, so a 1.65. So we should be good to go here. 1.65 times 250, and then we divide that by 25, and we square it. So 272.25, and just as we discussed in class, that 0.25 means we need more than 272. So that's going to be 273. Okay, so we need 273 here. Yep. Okay, and then so Luke wants to use a 99% confidence interval. So yeah, I mean, you know how it is with projects. You've got two different people have slightly different ideas about things. So Luke wants a 99% confidence interval. Without calculating the actual sample size, determine whether his sample should be larger or smaller than Raina's, and explain your reasoning. Well, if you want more confidence, but with the same margin of error, then you're going to need a larger sample size, right? More confidence means a better interval, right? So that's going to cost you, right? Let's see here. So sorry, I was looking at the wrong question. So it says no, the sample should be larger. Yeah. So yeah, we'll need a larger sample, right? Because we have higher level of confidence. Okay, and then calculate the minimum. So the answer is larger, right? So then calculate the minimum required sample size for Luke. Okay, so we know it's going to be more than 273, but just based on common sense, right? But to actually calculate that number, then we'll need the formula, right? So let's pull the formula over. So we go n greater than or equal. So we have the same margin of error of 25, same standard deviation 250, but because we're bumping up the confidence level to 99%, we'll now need 2.58 for the critical z-score, right? The z-star, right? So we go 2.58 times 250. Okay, then we divide that by 25, and we square it. So 666. Okay, so you can see what happens when you get a more confident, a higher level of confidence. You have to pay for it, right? Okay, I mean it's gonna cost you. You need to talk to about 400 more people to go from 90% confidence up to 99% confidence. Okay, so that's where the kind of the real world trade-offs come in. You start to think, well, okay, I can't afford to talk to that many people, so we'll have a smaller level of confidence or something, right? Okay, good. Does that help on that one? Good. All right. Anything else, guys? Anything else I can help you with? All right. Well, have a good one. Thanks, Julia. Take care, everybody. I'll see you on Thursday.